First, we'd like to talk about even and odd functions, their graphs, their symmetry, and how we're going to determine if they're even and odd algebraically. The two types of functions are even functions and odd functions. And we want to take a look at an example of a graph. This is not the only even function and the only odd function, but even functions could possibly look something a little bit like this. Notice that with the even function we have symmetry, and it's symmetric with respect to the y-axis. Okay, another way of thinking about that is that you could fold over the y-axis. The two sides would be kissing or touching. So here's your y-axis. And if I fold it on there, this side on the left would match up to this side on the right, and therefore there is symmetry there. Before we talk about the algebraic determination, let's take a look at what an odd function might look like. Just one example of an odd function would be a graph like this. Odd functions are symmetric with respect to the origin. So what does that mean? Well, it's not just as easy as folding over the y like the even function. In this case, we have to fold over the x-axis and then again over the y-axis. And if you fold over the x-axis and the y-axis, then the two branches would meet up. So over the origin here, notice this branch right here, if I folded over the x, would come up above the x-axis, and then if I folded it again over the y, then the two branches would meet. And that's the symmetry of an odd function. Now let's take a look at the algebraic determination. If f of x is our function, and we would like to find out if that function is even or odd, the thing that I'm going to do is I'm going to try to find out what f of negative x is, or f of the opposite of x. If f of negative x is equal to f of x for all x in the domain, then we can say that the function is even. What does that mean? Well, when I plug in negative x to the function, if all the signs stay the same, and I'm going to put that here, and all terms stay the same, then the function is even. Now, if I do f of the opposite of x, or f of negative x, and it turns out to be the opposite of f of x, or negative f of x for all x in the domain, then we can say the function is odd. So if I evaluate f at negative x, and all of my terms have the opposite sign, then I know that my function is odd. Now, in some cases, when you take f of negative x, it does not equal f of x, meaning it's even, and it doesn't equal negative f of x, or odd. So some of the signs might be the same, some of them might be different, and in that case, the function is neither even nor odd, which is a possibility. Next, we're going to algebraically determine if the following functions are even, odd, or neither. As we said earlier, we're going to evaluate f of the opposite of x in order to determine if this function is even or odd or neither. So every time I see x, I'm going to replace x with the opposite of x. Negative x squared is going to get me x squared. And I'm left with 3x squared plus 1. Next, I would like to compare f of negative x with f of x. Is f of negative x equal to f of x? Well, in this case, yes, 3x squared and 3x squared plus 1 plus 1, everything exactly the same. The signs are all the same, all the terms are the same. So we can say f of the opposite of x is equal to f of x. And if we look above, we remember that if f of x equals f of negative x, then my function is an even function. For the next function, f of x equals 4x cubed minus x, again I'm trying to evaluate at f of negative x. Every time I see an x, I'm going to substitute in negative x. Negative x cubed means negative x times negative x times negative x, which gets me a negative x cubed. Negative times a negative is a positive x, and I'm left with negative 4x cubed plus x. Next, I want you to compare f of negative x with f of x, the original problem. Are all the signs and terms the same? Well, no. Are all the signs different, yet all the terms the same? Well, yes, it is. Negative 4x cubed is the opposite sign of 4x cubed. Positive x is the opposite sign of negative x. Therefore, f of negative x is equal to the opposite of f of x. Every single term has the opposite sign. So that tells us that my function is odd. On our last problem, f of x equals x to the fifth plus 1, I'm going to evaluate at f of negative x. Plug negative x in for every x in the problem. Negative x to the fifth means negative x times negative x times negative x times negative x times negative x. That's 5 times. Because 5 is odd, it keeps its negative value. So f of negative x is equal to negative x to the fifth plus 1. Next, I'd like you to compare f of the negative x with f of x. Are all the terms the same? Yes. Are all the signs the same? Well, we have x to the fifth and negative x to the fifth. That means they're opposite signs, whereas the 1 is the same sign. Do all the signs change? No. Do all the signs stay the same? No. So this function is neither even or odd. Similarly, we can use possible symmetry to determine whether the graphs are even, odd, or neither. We said that even functions have symmetry with respect to the y-axis. Odd functions have symmetry with respect to the origin. And if it has any other symmetry or no symmetry at all, it would neither be even nor odd. So looking at these 3 graphs, the first graph, I can tell, has symmetry with respect to the y-axis. If I folded this graph along the y-axis, the yellow part of the graph would meet up with the green part of my graph, and they would be touching. Because we have symmetry with respect to the y-axis, I know that my function is an even function just by looking at the graph. On the second graph, we don't have symmetry with respect to the y-axis. We don't have symmetry with respect to the x-axis either. But if I folded it over the x-axis and the y-axis at the same time, then this yellow part of my graph, when reflected over the x and then reflected over the y, would also be matched up with the green part of my graph. Therefore, I have symmetry with respect to the origin. And if I have symmetry with respect to the origin, I know that my function is odd. On the last example, I have symmetry with respect to the x-axis. Notice that the yellow part of my graph, when folded over the x-axis, would match up with the green part of my graph. So I have symmetry with respect to the x-axis. Well, that's nice that we have symmetry with respect to the x-axis, but I don't have symmetry with the y, I don't have symmetry with origin. Therefore, I can not be classified as odd or even. I'm neither odd nor even. And if you take a little bit closer look at this graph, you can tell, if you pass a vertical line through it, that it does not pass the vertical line test. This graph is not a function at all. And if it's not a function, then clearly it couldn't be an even or an odd function, because it's not even a function at all. So that's one way to help you out with the symmetry over the respect to the x-axis. You might think, oh, was that even or odd? Well, it's neither, because it's not even a function at all.